picture this. You're cruising down the highway in a high-powered electric vehicle. You're doing, say, 70 miles per hour, maybe listening to some music, just completely relaxed.
Right, smooth sailing.
Exactly, smooth sailing. But under the floorboards, the central processing unit of your dual motor controller, which is, the thing literally dictating how much power is surging to your wheels, it just goes completely inexplicably crazy.
Oh, boy. Yeah.
And unlike a broken bone where you can just, you stop, get an x-ray, have a doctor point to the problem, there is no doctor in the car. There's no time for that.
No, absolutely not.
The vehicle has to basically diagnose its own catastrophic brain failure and physically pull the plug before you crash.
And we are not talking about human reaction times here.
Right.
We're talking about a time frame so small, it's almost impossible to conceptualize.
Yeah, it's wild. And that is our mission for this deep dive today. We are unpacking a highly technical engineering document that reads less like a car manual and more like a blueprint for a high-tech fortress.
It really does.
It outlines the ultimate safety net for electric vehicles, specifically focusing on achieving what's called the ASIL D safety standard, which, what is that exactly?
So ASIL D stands for Automotive Safety Integrity Level D.
Okay.
In the automotive industry, it is the absolute highest, most stringent level of hazard risk management that exists.
The absolute highest.
Right. It is exclusively reserved for systems where a failure could lead directly to severe, life-threatening injuries. So we're talking about things like your steering, your braking, and in this specific case, the motor control unit.
Okay, let's unpack this. Because to truly understand the scale of what these engineers are up against, we have to look at the core metric of this entire document, an acronym, FTTI, which stands for Fault Tolerant Time Interval.
Right. The FTTI is essentially the ticking clock of survival. If that motor controller's brain goes haywire, the system has exactly 10 milliseconds or less to identify the failure.
10 milliseconds.
Less than or equal to 10 milliseconds, yeah. And in that time, it has to cut the inverter's power and force the vehicle into a safe state.
I mean, 10 milliseconds, that is...
To put that in perspective, a human blink takes about 300 milliseconds.
Wow.
So in roughly 1/30th of the time it takes you to just blink your eyes, this system has to realize it's suffering a catastrophic software failure, completely bypass its own processing core, and physically sever the power to the wheels.
That's insane. So less than or equal to 10 milliseconds is the golden rule here.
Yeah, that's the baseline.
And we're going to keep coming back to that. But before we can appreciate the defense systems these engineers have built to guarantee that reaction time, we really need to understand what they are defending against. Like, what is actually attacking the system?
That's where things get really fascinating.
Yeah.
Because we aren't just talking about, a programmer making a typo in the code.
Right.
The threats that can crash this main microprocessing unit, and the document references an advanced automotive chip called the AURIX TC3XX. These threats are physical, environmental, and frankly, they're inevitable.
Yeah, looking at the engineering specs, they point out 4 major attackers, and honestly, they sound like something out of a sci-fi movie.
They do.
Let's look at the first one, which actually comes from the car itself. Electromagnetic interference, or EMI.
Yeah.
What I found crazy in the research is just how violent the electrical environment inside an EV really is.
It is incredibly hostile. Modern electric vehicles rely on components called SiST MOSFETs.
Right, silicon carbide.
Exactly. SiST stands for silicon carbide, and a MOSFET is basically an incredibly robust electronic switch. Its job is to take the direct current, the DC power from the battery, and chop it up.
Chop it up to make AC power, right?
Right, turning it on and off thousands of times a second to create the alternating current, the AC power, that actually physically spins the motor.
And the document notes that these switches operate at blistering speeds. It says the voltage change over time, the dVdt, is greater than or equal to 10 kilovolts per microsecond.
Yep.
Let's just ground that for a second. 10 kilovolts per microsecond. That is like turning the power of a minor lightning bolt on and off 1,000,000 times a second.
That's a perfect analogy. And when you switch that much voltage that fast, it creates a massive electromagnetic shock wave.
Just purely from the switching.
Yeah.
Yeah.
It is pure, intense radiation radiating outward from the power electronics.
And according to the specs, this radiation literally bleeds over into the delicate computer lines. It couples into the clock lines of the processor, causing something called clock jitter, which makes the watchdog timer, the safety monitor, drift.
Right. Think about the processor's clock as a metronome. The whole computer relies on that steady beat to execute commands in order.
Okay.
Now imagine you blast a blinding strobe light in the face of a musician who's trying to follow that metronome.
They'd get completely disoriented?
Exactly. The electrical noise from the motor literally disrupts the physical rhythm of the processor that is trying to control it.
So the very act of driving creates radiation that tries to deafen the car's brain.
Precisely.
Okay, so that and an internal threat. But the second threat comes from the outside, and this is the one that really, it made me pause when I read it. Cosmic radiation.
Oh, yeah.
Specifically, high-energy atmospheric neutrons, or even alpha particles decaying right out of the plastic packaging of the microchip itself.
Yes, this is known as the single event effect.
Wait, I have to push back here, because when I read this, it felt a little, I don't know, paranoid?
Sure.
Are automotive engineers really sitting around worried that atmospheric space particles are going to snipe our cars and cause crashes? I mean, why is this a real threat?
I know, it sounds absurd until you look at the scale of modern microelectronics.
Okay.
Inside that processor, you have SRAM, static random access memory. Think of SRAM as billions of microscopic buckets holding electrical charge.
Buckets of charge. Got it.
Right. A full bucket is a 1, an empty bucket is a 0. Because these chips are so incredibly small now, the buckets hold a tiny, tiny amount of charge.
Okay, so the buckets are super sensitive.
Exactly. And the Earth's atmosphere is constantly bombarded by cosmic rays, which break down into high-energy neutrons.
Right.
If a single neutron traveling at high speed physically strikes one of those microscopic buckets, it can inject just enough charge to flip a 0 to a 1.
Just randomly flips a bit of memory, just from one particle hitting it.
Right. And if that specific bit of memory happens to be part of the program counter, which is the instruction telling the CPU exactly what to do next, the computer suddenly jumps to a random, invalid memory address.
Oh, wow.
Yeah. It falls into what they call a dead loop or causes a stack overflow. The software is instantly corrupted by a physical strike from a subatomic particle.
It's literally a microscopic space bullet hitting the car's brain.
That's exactly what it is.
And the watchdog timer, which relies on the CPU running normally, it just starves to death because the CPU is stuck in this loop.
Yep, the timer just runs out.
Wow. Okay, so threat number 3 is completely different. This one is a pure logic problem called task deadlock. The technical architecture points out that the real-time operating system, or RTOS, can basically choke on its own math.
Yeah. To understand this, we have to look at how a real-time operating system actually manages tasks.
Okay.
Unlike your home computer, which might just stutter a bit if you open too many browser tabs, an RTOS in a car has strict life-or-death priorities. Running the brakes is high priority. Updating the radio display is low priority.
Makes total sense. But the document describes a scenario called priority inversion. It mentions this happening during complex multi-source fault diagnostics.
Right. Priority inversion is a classic, terrifying software architecture problem. Imagine a 3-lane highway.
Okay, a highway.
You have an ambulance, which is our high-priority safety task.
Right.
You have a slow-moving street sweeper, which is our low-priority watchdog task.
Got it.
And you have a bunch of regular sedans, which are medium-priority tasks.
Okay, I'm with you. Sweeper, sedans, ambulance.
Now, imagine the slow street sweeper grabs the only key to a specific gate on the highway. It needs to get through, do its job, and return the key.
Right.
But suddenly, a ton of medium priority sedans flood the highway. The system rules say medium priority sedans always get to drive before low priority street sweepers.
Oh, I see.
So the sweeper is completely blocked.
But the sweeper still has the key to the gate.
Precisely. And now the ambulance, the high priority task, rushes up. It needs to get through the gate, but the street sweeper has the key and isn't allowed to move.
Because of the sedans.
Right. The entire system gridlocks.
It's like getting so obsessed with solving a really complex math puzzle that you literally forget to breathe.
Yes.
The system gets hyper-focused on all these intermediate calculations, the sedans, and the basic survival mechanism, the watchdog, gets completely ignored and starves.
Exactly.
Not because of a space particle, but because of a logical traffic jam.
The code essentially suffocates itself.
Which brings us to the fourth attacker, SPI communication chaos. And this loops right back to that massive electromagnetic noise from the battery switches we talked about earlier.
Right, the EMI.
The setup is this. You have the main processor, the MCU, and you have a separate external safety chip called the SBC. They talk to each other over a bridge called the SPI bus.
Think of the SPI bus as a walkie-talkie channel between the main brain and the safety monitor.
Right, but because of that 10 kilovolt per microsecond shockwave, The noise on the walkie-talkie channel is just deafening.
Yep.
The safety chip asks the main brain a question, but the answer gets scrambled by the EMI noise. And the source document notes this causes CRC errors. What is a CRC error?
So CRC stands for cyclic redundancy check. It as a mathematical way for the receiver to verify that the message wasn't corrupted in transit.
Okay.
If the safety chip calculates the CRC and it doesn't match what was sent, it knows the message was scrambled.
And the rule here is 3 strikes. If the safety monitor gets 3 scrambled messages in a row because the noise is too loud, it assumes the main brain is dead and triggers a reset.
Exactly.
So we've got blinding electrical noise, microscopic cosmic bullets, mathematical suffocation, and walkie-talkie chaos. Any one of these can freeze the motor controller at 70 miles per hour.
Yeah.
Since these attacks are basically inevitable, how does the vehicle catch them before that 10-millisecond window closes? This moves us into the second dimension of the document, the architecture.
Right, the architecture and software-hardware co-diagnostics, because automotive engineers don't just build one wall to keep these threats out.
They need more than that.
They rely on defense in depth. It's a multi-layered, heavily redundant fortress of checks and balances.
Okay, let's walk through these fortress walls. Layer 1 is the internal dual watchdog. I actually thought this was brilliant. The MCU doesn't just have one watchdog, it has 2. The primary one runs on the system's main clock. But the backup watchdog runs on a totally independent internal RC oscillator. What makes an RC oscillator so special?
It comes down to physical robustness. Most primary clocks use a quartz crystal oscillator.
Like in a watch?
Exactly. They are highly precise, but they are physical crystals. If you hit a massive pothole, the physical shock could actually fracture the crystal, stopping the clock entirely.
Oh, wow.
Furthermore, we already know EMI can cause jitter in that main clock line.
So if the main clock gets scrambled by noise or physically breaks because of a pothole, the primary watchdog is just useless.
Exactly. But an RC oscillator, which stands for resistor capacitor, doesn't use a fragile vibrating crystal.
Okay.
It generates a heartbeat simply by charging and discharging a capacitor through a resistor. It's built directly into the silicon, it's highly temperature resistant, and it is completely isolated from the main clock.
That is smart.
Yeah. Even if the rest of the processor goes totally dark, that RC heartbeat keeps pumping, and it will trigger the alarm.
That is serious redundancy. Okay, so layer 2 is the external Q&A watchdog, and this is run by that external safety chip we mentioned, the SBC.
Right.
Here's where it gets really interesting to me. It's not just a simple ping like, "Are you there?" The technical specs describe it as a dynamic game of cryptographic ping pong.
This is a massive leap over older safety systems. A traditional watchdog is just a countdown timer.
Like a microwave timer.
Yeah. As long as the processor sends a quick signal to reset the timer before it hits 0, everything is assumed to be fine.
But if the processor gets stuck in a loop, couldn't it just accidentally keep hitting the reset button? Like a bird pecking a lever?
Exactly. The lights are on, but nobody is home. That's why they moved to a question and answer mechanism.
The document says the SBC sends over a random token, and the main processor has to use an AES-128 or LFSR math unit to calculate a reply.
Yep.
So it's basically advanced cryptographic math. It's the same kind of encryption that secures your online banking. It's like think of it like a bouncer at a high-stakes spy club.
I love that analogy. Go on.
The bouncer doesn't just ask to see your ID. He slides you a complex, completely random cryptographic math problem. You have to solve it and hand it back.
Right.
But it's not just about getting the right answer. You have to reply within a strict open window.
This is crucial.
The specs say if you answer too early, it's a fault. If you answer too late, it's a fault.
Which proves multiple layers of sanity.
How so?
Well, if you answer too early, the safety chip assumes you aren't actually doing the complex math and are just spitting out pre-calculated garbage. Maybe a robot or a stuck loop.
Oh, that makes sense.
If you answer too late, your processor is bogged down and failing. You have to give the exact right mathematical answer in the exact right millisecond.
And 3 wrong answers, and the bouncer throws you out.
Meaning a hardware reset. Exactly.
That is incredible. Which brings us to layer 3, the AUTOSAR WDGM, or Watchdog Manager. This is a purely software-based check. The research details how it sets up sentinel checkpoints to track the logical flow of the code. So, for example, the software dictates that step A must go to step B and then to step C.
This is a direct defense against those cosmic rays we talked about.
The space bullets.
Right. If a neutron flips a bit, the program might jump from step A directly to step F. The software watchdog monitors the sequence, realizes the logical flow is broken, and raises the alarm.
And it also monitors temporal flow, right?
Yes.
So if a task that normally takes 100 microseconds suddenly takes 200 microseconds, it knows that priority inversion traffic jam has happened.
Exactly. It catches the deadlock.
But wait, I need to push back here, because layer 4 of the architecture is hardware gating. This is the ultimate failsafe.
Yes, the guillotine.
Right, the guillotine. The document explicitly states that if a fault is confirmed, the external safety chip bypasses the main CPU entirely. It uses physical copper hardwires to cut the gate drive power within 1 millisecond.
Yep.
It physically blocks the PWM.
Mm-hmm.
So my question is, if we have a physical hardwire that can just pull the plug in 1 millisecond, why are we spending so much computing power on software checkpoints and cryptographic bouncers?
Right.
Why not just use the hardware switch?
Because software is inherently malleable, which is both its greatest strength and its fatal flaw. If you rely purely on software to shut down a frozen computer, you're asking a broken brain to fix itself.
Which doesn't work.
That's why bypassing the CPU to cut power via physical hardlines is the purest form of fail-safe engineering.
But we still need the software layers first.
Yes, for escalation. You use the software watchdogs to catch subtle, logical anomalies early before they escalate into a total system lockup.
Ah, okay.
But the final layer, the hardware gating, is there for when the core is totally compromised. You mentioned blocking the PWM.
Right, pulse width modulation.
Think of PWM as the electrical throttle signal telling the motor how fast to spin.
So by physically blocking the PWM signal on a hardware level, you are instantly slamming the throttle shut, regardless of what the crazy software is trying to do.
Exactly. It absolutely guarantees that less than or equal to 10 millisecond shutdown.
Okay, so the multi-layered architecture makes complete sense. We've mathematically and logically solved the problem on paper, but paper doesn't drive down the highway.
No, it doesn't.
How do engineers stop the physical circuit board itself from degrading over time and letting these attacks slip through?
Yeah.
This takes us into the third dimension of the document, the design phase, what the automotive industry calls DFMEA.
Right. Design failure mode and effects analysis. This is where we look at designing the physical armor.
Because a perfect software architecture is useless if the board melts.
Exactly. If the physical copper and silicon can't withstand the extreme thermal and electrical environment of an EV, the software doesn't matter. Engineers have to anticipate physical degradation.
The specs outline 3 major design preventions baked right into the board. First is the hardware clock monitoring unit, the CMU. We talked about having a backup RC oscillator. The CMU constantly compares the main clock to that backup. If there's even a 2% drift between them, it triggers an unmaskable interrupt.
An unmaskable interrupt, or NMI, is a fascinating piece of processor architecture.
How so?
Well, in normal operation, a CPU can mask, or basically ignore, certain alarms if it's busy doing something more important.
Like hitting snooze on an alarm clock.
Exactly. But an NMI is hardwired to be impossible to ignore. If the clocks diverge by 2%, it means the physical timing of the chip is compromised, perhaps by that intense EMI we discussed.
Right.
The NMI forces the CPU to drop literally everything and immediately jump to a safe state shutdown routine.
No snooze button allowed.
None.
The second design prevention directly tackles that massive EMI radiation, that 10 kilovolt per microsecond shockwave from the battery switches. It's called SPI anti-EMI design.
This is crucial for that walkie-talkie channel.
Right. To protect that channel, the engineers use differential routing, common mode chokes with over 2,000 ohms of impedance, and Class 1 C0G capacitors on the printed circuit board.
That's a mouthful.
It is. It says this guarantees zero data distortion. But how does that actually work in plain English?
Let's break down differential routing first, because it is a brilliant physical trick. Instead of sending the walkie-talkie signal down a single wire, you send it down 2 parallel wires side by side.
Okay.
But here's the trick. On the second wire, you send the exact inverse of the signal.
So if wire A sends a positive pulse, wire B sends a negative pulse at the exact same time.
Right. Now, when that massive wave of electromagnetic noise washes over the board, it hits both wires equally. It adds the exact same amount of garbage noise to both signals.
Okay, I see where this is going.
When the receiver at the other end gets the 2 signals, it simply subtracts wire B from wire A. Because the original signals were opposites, they combine perfectly, but the external noise, which was identical on both wires, mathematically cancels itself out to 0.
It's literally noise-canceling headphones for the circuit board.
That is exactly what it is.
The noise is subtracted out physically.
Yeah.
And what about the chokes and capacitors?
Those are physical filters. A common mode choke creates high electrical resistance or impedance, specifically against that high-frequency garbage noise, blocking it from traveling further down the line.
Okay.
And C or G capacitors are incredibly stable across extreme temperatures, ensuring the filters don't drift whether it's freezing outside or the motor is actively overheating.
Amazing. And the third design prevention is for those cosmic space bullets we talked about. SCC ECC memory armor.
Yes!
The document notes that all the SRAM has error correction code built in.
SCC DED stands for Single Error Correction, Double Error Detection.
Wait, I really need to understand the mechanics of this. If a cosmic ray flips a memory bit from a 0 to a 1, how does the computer possibly know it was supposed to be a 0? To the computer, it just looks like a perfectly valid one now.
That is the magic of parity bits. The system doesn't just store your data, it uses extra hidden bits of memory to store a mathematical summary of that data.
Like a checksum.
Sort of. Imagine you have a row of numbers, and at the end of the row, you write down whether the sum of those numbers is even or odd.
Okay.
If a cosmic ray changes one of the numbers, the new sum won't match your even or odd note at the end.
Ah, so it instantly detects that something was tampered with.
But SECD goes a step further than just detection. By using a complex matrix of these parity bits, the math doesn't just know there's an error, it can geometrically pinpoint exactly which bit was flipped.
Wow.
And because it's binary, if it knows a specific bit is wrong and it's currently a 1, it mathematically knows it must be a 0. It flips it back, healing the memory on the fly before the processor even realizes a cosmic ray hit it.
It heals itself instantly. That is mind-blowing.
It's beautiful engineering.
But listening to all of this, the differential routing, specialized temperature-resistant capacitors, self-healing memory matrices, I have an obvious question here.
Sure.
This sounds incredibly complex and mathematically heavy. If electromagnetic noise and space radiation are such existential threats, why jump through all these mathematical hoops? Why not just build a tiny, thick lead bunker around the processor, put it in a Faraday cage, and physically block all the radiation?
It's a very logical question, but you have to remember the context. We are building an electric vehicle.
Right.
In an EV, weight and physical space are absolute non-negotiable premiums. Every extra pound of lead shielding you add directly reduces the car's driving range.
Right. Battery efficiency. You want the car to go as far as possible.
You simply cannot use heavy lead shielding. So automotive engineers are forced to solve physical problems with math and geometry rather than sheer mass.
That's a great way to put it.
They use the geometry of the differential wires and the mathematics of the SEC memory to create a virtual shield that weighs absolutely nothing.
Math and geometry over mass. I really like that. Okay, so the blueprint is flawless.
Yeah.
The design armor is set.
Yep.
But a blueprint is just paper, and a mathematical model is just a simulation. How do they ensure that a factory robot on a massive assembly line builds this highly sensitive device correctly every single time?
This brings us to the fourth dimension, the manufacturing phase. What engineers call PFMEA, or Process Failure Mode and Effects Analysis.
Because you can have a perfect design, but if a solder joint is weak, the whole system fails.
Exactly.
And the factory controls outlined here are intense. The first one is 100% 3D AXI voiding gating. The specs say that every single main processor and safety chip undergoes a 3D X-ray or ultrasound scan immediately after it's soldered to the board.
Every single one.
The requirement is that the total solder void rate, meaning the microscopic air bubbles trapped inside the molten solder, must be less than or equal to 5%, with a maximum single void size of 1%. Why are we X-raying for tiny air bubbles?
Because solder voids are a silent, delayed killer in automotive electronics.
How so? Why are they so dangerous?
Imagine you have a tiny air bubble trapped in the metal connecting the chip to the board. When you drive down the road, your car experiences constant high-frequency vibrations.
Just from the road surface.
Right. Over thousands of miles, that vibration stresses the metal. The air bubble acts as a structural weak point, and eventually a microscopic crack forms.
Okay.
As you keep driving, freezing in winter and baking in summer, the metal expands and contracts, widening the crack until it completely severs the electrical connection.
And suddenly the physical wire connecting your clock or your SPI walkie-talkie channel just snaps.
Exactly. And you have a catastrophic failure on the highway, months or years after the car left the factory.
It's like an obsessive dentist taking a 3D X-ray of every single tooth in your mouth, every single time you brush, just to make sure there isn't microscopic cavity forming.
That's a vivid way to picture it.
I was looking at these manufacturing specs, and it blew my mind that they are literally X-raying every chip on the assembly line.
Hmm.
I thought that level of scrutiny was reserved for aerospace.
And that realization points to a massive shift in how we view consumer transportation today.
Yeah.
Think about it. If the motherboard on your laptop has a bad solder joint and it freezes, it's highly annoying. You lose an hour of work, you restart it.
Right. No big deal.
But if the dual motor controller freezes at 70 miles per hour, lives are instantly on the line. An EV is essentially a low-flying, extremely heavy, high-voltage aircraft.
Wow.
The automotive industry has had to adopt aerospace-level quality controls because the operational environment is just as harsh and the consequences of failure are just as severe.
That reality check leads perfectly into the second factory control I want to highlight. End-of-line, or EOL, fault injection.
This is a fun one.
Before a controller is packed up and leaves the factory, the testing machine literally hacks the board. It injects code specifically designed to crash the processor and block the watchdog timer. And then it physically measures the response time.
It measures whether the hardware gating guillotine actually drops in less than 10 milliseconds.
Exactly. And if it takes 11 milliseconds, the MES, the manufacturing execution system, literally refuses to print a passing label for that unit. It just gets scrapped.
Think about the confidence that requires. They don't just test if the device boots up and spins a motor. They intentionally execute a catastrophic disaster scenario on every single unit rolling off the line.
Right.
If it can't save itself on the factory floor, it doesn't ship.
And finally, to ensure no one messes with the software after it passes that test, they flash bootloader SHA 256 digital signatures to guarantee the firmware is completely tamper-proof.
Gotta keep it secure.
So the unit has survived the attackers, theoretically. It's wrapped in mathematical design armor, and it has passed the obsessive 3D X-rays and hacking tests on the factory floor.
But before a new controller design is allowed to enter mass production, prototypes have to survive validation testing.
Right, moving to the fifth and final dimension, the torture chamber. This is DVP&R, or Design Verification Plan and Report. This is where engineers prove that their math and X-rays actually hold up in the real world.
Yeah, the rubber meets the road here.
The validation tests outlined here are absolutely brutal.
They are trying to compress 10 years of extreme physical abuse into a few weeks of testing.
And let's look at test number 1, high-load EMI. They hook the controller up to a motor and run it at a massive 12,000 RPM.
Screaming fast.
They inject 200 milliamps of raw current directly into the system and blast the entire setup with 100 volts per meter of electromagnetic radiation. The acceptance criteria: 0 lost packets on the SPI bus. 0 fake resets.
100 volts per meter is an astronomically high electromagnetic field.
Is it?
Oh, absolutely. It is designed to test the absolute limits of those differential routing lines and noise-canceling capacitors we talked about earlier. They are essentially screaming at the processor, trying to drown out the safety monitor's walkie-talkie channel with pure noise, while the motor is spinning at maximum velocity.
And it has to just keep doing the cryptographic ping-pong flawlessly.
Exactly, without missing a beat.
Okay, test number 2, shake and bake. They bolt the controller to a machine and subject it to 1,000 hours of 3-axis random vibration. The acceleration force is 35 meters per second squared.
Yep.
And while it's violently shaking, they cycle the ambient temperature from negative 40 degrees Celsius up to a blistering 125 degrees Celsius.
So 35 meters per second squared is roughly 3.5 Gs of force, shaking the board randomly in all directions.
That's violent.
Extremely. Now, combine that with thermal shock. When you go from negative 40 to 125 degrees, the circuit board, the microchips, and the copper traces all expand and contract at slightly different rates.
Because they're different materials.
Right. This thermal mismatch is designed to physically tear apart weak solder joints.
But the acceptance criteria is wild. After 1,000 hours of this, the contact resistance across the board can only change by a maximum of 1.2 milliohms.
Which proves that the 5% voiding limit from the 3D X-rays actually works. By keeping the air bubbles out of the solder, the metal remains strong enough to survive a lifetime of violent shaking and extreme temperature swings without cracking.
It's all connected. Which brings us to the final test, the grand finale of the torture chamber. Hardware in the loop, or HL, fault injection.
This is the ultimate test.
They are running the motor at full tilt, 12,000 RPM. And while it's screaming away, they intentionally short out the crystal oscillator, or they inject a dead loop into the code. They basically murder the brain while it's running at top speed.
And we know what has to happen here.
Right.
The entire multi-layered architecture, the internal watchdogs, the Q&A tokens, the hardware gating, all of it must recognize the failure and drop the guillotine in less than or equal to 10 milliseconds.
And it does.
Yeah.
But here's the kicker, the ultimate goal of all of this. The spec says that during that shutdown, the torque fluctuation at the wheels must be less than 5 Newton meters. The system must smoothly transition the motor into a free-coasting active open-circuit state with absolutely zero wheel lock.
This is the critical moment. This
That's
right
all.
here is why the 10 millisecond rule exists in the first place.
So what does this actually mean for the driver? Well, let's visualize this.
Okay.
You're back on the highway driving at 70 miles per hour. The motor is spinning at 12,000 RPM. Suddenly, a cosmic ray hits the processor, or a software priority inversion deadlocks the system.
Right. The brain completely dies.
The brain dies. And the expectation, according to this entire engineering document, is that you, sitting in the driver's seat, barely feel a bump. A torque change of less than 5 Newton meters is virtually imperceptible. The car just gracefully cuts power and glides into a coast.
Avoiding real lock is the absolute pinnacle of automotive safety engineering.
Because if they lock,
If you were doing 12,000 RPM on an electric motor and the processor fails in a way that accidentally locks the inverter's electrical phases, the motor instantly freezes.
oh man.
If the motor freezes, the wheels lock up instantly. At highway speeds, if your wheels lock, the vehicle violently spins out of control. It is catastrophic.
So the entire 10 millisecond reaction time isn't just about turning the computer off. It's specifically calibrated to catch the failure before the electrical phases have time to cross and lock the motor.
Precisely. The dual watchdogs, the ASIL D self-healing memory, the physical hardwire guillotine switch, every single layer exists to ensure the motor is allowed to freewheel gracefully. It is quite literally the difference between a minor roadside inconvenience and a fatal accident.
Wow. Let's just take a breath and recap this journey, because the sheer scale of engineering here is astounding.
It really is a marvel.
We started by looking at invisible threats, high-speed cosmic neutrons from space, and blinding electrical noise from the car's own high-voltage battery switches.
Yep.
We saw how engineers fight back with a multi-layered fortress of internal dual watchdogs, spy movie cryptographic tokens, and a physical 1 millisecond guillotine switch. We explored how they use mathematical geometry and self-healing memory to save weight instead of using heavy lead shields.
Defense in depth.
Right. And we learned that they 3D X-ray every single microscopic solder joint to aerospace standards and subject the final product to thermal, vibrational, and electromagnetic torture chambers. And every single piece of this massive puzzle exists just to guarantee a reaction time of less than or equal to 10 milliseconds. All so that if the brain fails, you just safely coast to the side of the road.
It is a phenomenal testament to modern automotive engineering. But, buried at the very end of the research materials, there is a fascinating little detail that I think points directly to where this industry is heading next.
Oh, what caught your eye?
The author of the technical document offers a service at the end. They offer to use advanced Python simulation tools to model this exact EMI coupling, the clock jitter, and the time window margins dynamically for other engineers.
Okay.
They are offering to build a highly complex transient dynamic coupling simulation model just to figure out the exact mathematical tolerance of a single watchdog timer.
Okay, wait. If engineers are having to build incredibly complex dynamic Python simulation models just to figure out if a watchdog timer is going to work in a single motor controller, think about what happens when we move beyond individual cars.
Exactly.
As we enter the era of fully autonomous vehicle networks, or even electric flying taxis, the amount of invisible noise, cosmic radiation targets, and software variables will multiply by thousands.
That is the frontier. As the complexity of the central brain scales up into artificial intelligence and neural networks driving our cars, the complexity of the watchdog monitoring that brain must scale exponentially just to keep up.
Will our current physical fail-safes and cryptographic ping-pong games be enough? Or will AI have to start designing the watchdogs that watch the AI?
It's a great question.
It is a wild thought to ponder the next time you're cruising at 70 miles per hour, trusting the invisible fortress under the floorboards. Keep questioning, keep learning, and we'll catch you on the next deep dive.